Hello, everyone. Welcome to our seminar. Today we are very happy to have Wei Wu from New York University, and he will talk about massless spaces for building model.
Okay, thank you so much, Xin, and thanks a lot for the invitation. It's very nice being here. So today, technically I'm talking about a pre-COVID research project with Paul, and after our work has been online, we experienced a lot of kind of dramatic things happen, like lockdowns, and so Paul has moved from Israel to France, and both of us gave some online talks, but it's really the first time to give an offline talk about this 2 years. So I apologize for those of you who have attended the talks online before. So the whole work has been came out of. Sorry about this. The work has been came out of a lot of inspiration from the discussion with Tom, and in fact, it's been the subject that Tom and Kosterlitz has made a great contribution to. And for some specific model, we are able to give a precise result, which is improves our understanding of these asymptotics. So I'm going to focus on the delay model today, but just a comment that this belongs to a universality called the obedience spin models. There are other prominent examples there, XY model, clock model, or U1 lattice gauge theory. They should have the same universal behavior. It would be nice to extend some of these results to the other models. And a basic strategy we're using is we rely on the duality, and the duality would give you some kind of a Coulomb gas representation of the model. And then we go through renormalization, which give you something which is more doable when you integrate out shorter scales. And then we rely on techniques of the Helfer-Sylstra representation and some PE techniques. Okay, we'll be more specific about this. So, so here's a classical XY model. You just have a spin model where each particular point have a spin, taking value on the circle. Can write down the Gibbs measure. It's a very natural one. So the energy is given by the inner product of the nearest neighbors. So we can also parameterize by the cosine of the angle difference because they're on the unit circle. It's been of great interest in mathematical physics because the model has a very special kind of phase transition, especially in low dimensions. It's going to be helpful to understand, for the application of as a toy model for a lot of applications like superconductors, etc. And it's also so I'm writing down the Gibbs measure for finite volume, but you can also do that for an infinite volume. It's there is some monotonicity there. So, for example, there is this Geneva type inequality, which gives you some monotonicity of the spin correlations. So you can took the infinite volume limit without the problem. So that's the classical XY model. Now, what our work has been focused on is so-called Belin model, which is an approximation to the XY at low temperature. So at very low temperature, you would expect the spins tend to align with each other. So this cosine -1 thing is really small. So you can use the following approximation by the periodized Gaussians. So here, this is each one is like Gaussian, but you have to sum over some winding numbers around the circle. So the theta are angles, and you have to sum over the difference plus the winding number and taking the squares. So another way to interpret this is that this is the heat kernel on the unit circle. So now if you replace this XY interaction, beta SI dot SJ, by this heat kernel thing on the unit circle, that's the Belin model that you're getting. It looks a bit nicer because it has a lot of Gaussian thing in it. But again, if you look closerly, look at closely, it's still not log concave, right? Because you have a summation here. So if you took a log of that, it's not going to be a log concave function. So it still possesses a lot of challenge to understand the large scale behaviors. So these models exhibit a special kind of phase transitions. In particular, it's unlike the ferromagnetic, where phase transition is often associated with the symmetry breaking. In particular, in 2 dimensions, both of these models, none of these models have symmetry breaking at any temperature by the famous Mermin and Wagner theorem. And so in particular, you need to describe the phase transition in terms of so-called topological defects, which are vortices of the model. This is a celebrated BKT transition. In dimension 3 and higher, as will be more specific later on, it's a bit different. So at low temperature, you do have a symmetry breaking, prefer the direction of the spins, but on top of that, there is a so-called Gaussian mode, which is some kind of, mathematically speaking, some kind of a Gaussian free field of fluctuations on top of the symmetry breaking phase. All right, so this is one picture about the phase diagram in 2D. It's from a related model, not the XY, the sine Gordon model. For the XY, you can think of Z there is like infinity. So you can see that as predicted, there is a phase transition for the model. So if you zoom out on larger and larger scales, there is some renormalization flow going on. And at the low temperature, large beta phase, it will drive you to some free field fixed point with some effective beta. Okay, this is what happens at low temperature, but at high temperature, this renormalization line does not work, and you expect a mass gap here. So this is what was expected in 2D. In 3D, it's a little different, as we said. So you have a phase transition. There's a beta critical here. On one side, you have a mass gap, but on the other side, you have the long range order of symmetry breaking, and on top of that, you have the Gaussian mode. Okay, we'll be more specific about these statements later on. So what is the state of art for this case? Unfortunately, not well. So we still know quite little about these phase transitions in both in 2D and in 3D and higher. So what was known basically are pretty much away from the critical temperature. So we know some results for a small beta that you have mass gap. So that was the work by Michael and Simon. And for large beta, there were celebrated results by, this is in any dimension. For large beta, there are celebrated results by Tom and co-authors. For example, in 2D, there are upper and lower bounds for the spin-spin correlations by McBride and Spencer. And by Froelich and Spencer, which gave you unmatching upper and lower bounds for the spin-spin correlations.
I should say here, high temperature is a general theory by Dobrushin.
Sure, yes.
So
okay, maybe
I think which will somewhat improve the
maybe for even higher temperature, yes.
Right.
But here is Dobrushin's result.
Yeah.
For the XY model, your result with Barry gets quite close to the beta critical.
Yeah.
Remarkably close.
Closer.
Yeah.
I thought that Dobrushin should be there.
Right. Now in dimension 3 and higher, there's of course the celebrated work by infrared bound, Froelich, Simon, and Spencer, which give you the long range order. And the work I'm going to describe with my work with Paul is that we actually obtain a very precise asymptotics of the Gaussian mode on top of that. Okay, so let's be more specific here. So what is known in dimension 3 and higher? So using this infrared bound technique, one can show that the 2-point function at low temperature has a uniform lower bound. The G0 is the standard of Green's function on dimension 3 and higher, which is finite. So you see that for beta positive, you have a good estimate on the 2-point function lower bound. So this gives you long range order. Now, it's very natural to inquire what happens on top of that, right? So for example, you can think about 2-point function is uniformly positive. What about the truncated 2-point function? So now, here is the prediction on more physics ground, which could be attributed back to the Dyson, I guess. This is called the spin wave approximation. At very low temperature, you expect the angle difference are very small. So one can just expand the cosine to see that approximately to the first order, it's like a gradient square. If you took gradient square, it's just a Gaussian free field. So you can basically compute everything there. So that Gaussian computation would give you that the 2-point function is in 2 dimensions decays like a specific power law, 1/2 pi beta, and in dimension 3 and higher, it gave you of order 1 constant plus another constant divided by x to the minus 2. Now this picture is qualitatively correct, but not quantitatively. So basically you got the behavior. The correct behavior should have a different exponent here and a different constant here. And the reason for that is that by approximating by Gaussian, one ignores the occurrence of vortices. So these vortices came, sometimes you have a plus vortices like this, sometimes you have an anti-vortices. What happens at low temperature is they're going to tightly binding with each other. So on large scales, there sort of no, you still have a free field behavior, but this interaction of the vortices would somehow change your covariance structure for the free field. So that's the picture. And so back in the 70s, the Kosterlitz and Thouless have some non-rigorous argument, which I won't really go through, to show that the vortices behave like essentially like a neutral Coulomb gas. And they were also managed to integrate out the Coulomb gas scale by scale, obtain the famous renormalization flow of this these class of the spin models. This is the Kosterlitz-Thouless flow, which sort of fits with this predicted phase diagram here. Now, what was rigorously known? So the first thing is it still remains open, which is a very interesting open question to show that at low temperature in 2D, the spin-spin correlation has a power law decay, but the power is not the same as what you expect from the Gaussian computation. It should be something which has a correction from the vortices. This still remains open. Now, what was known there is that there's a work by McBride and Spencer, which shows there's an upper bound of the 2-point function. The upper bound is a Gaussian bound. Okay, so this is what you expect from the Gaussian computation. And more recently, there's this work by Galban and Sepulveda, which improves the upper bound by obtaining a decay which is a bit faster than this. But none of these were sharp. And for lower bound, there is this celebrated work by Tom and Joe Froelich, which gave you the lower bound of the 2-point function. Still doesn't really match the upper bound at every finite temperature. So in 2D, this spin-spin correlation question still remains open. There have been a lot of considerable progress in recent years for related models. So for example, there's a paper work by Falco using impressive renormalization group analysis, which can in fact prove such conjecture for the model of Coulomb gas and Stein-Gordon. So he obtained the precise 2-point function asymptotics at low temperature and even some correction at the critical temperature. For sine Gordon, this has been carried out by the work of Falco. And also fairly recently, there was a paper by Roland Bauschmidt, Park, and Rodriguez, who studied the discrete Gaussian model, which we'll see later. This is like somehow the dual model for the Villain model. And it's just a Gaussian free field that you have a value pinned down on the integers. This model has a well-known roughening transition. So if you have a beta large, you would expect the large scale behavior of the model behave like a continuum Gaussian free field. So they actually proved the central limit theorem for this model at this large beta. Now, this result should be quite closely related to the spin-spin correlation of the Villain model in 2D, except that if you go to this representation of duals, the spin-spin correlation for the Villain model is not something looks that nice in terms of discrete Gaussian. So you need to have a result for a more general test function, which is more singular and more nonlinear, in order to be able to prove the conjecture for the Villain models. Let me also mention that there's also a nice work by Michael and Ron and Jacob Shapiro, Martin Hariel, which sort of investigate this duality relation between the discrete Gaussian and the Villain model. And they have this comparison for the critical temperature. So as long as the discrete Gaussian have a variance, has fluctuation go to infinity, you would have a power law decay of the correlation function for this Villain model. So it's one-sided bound.
So well, it's worth mentioning that this is a question special in 2 dimensions. In 3 dimensions, this is wrong.
Yes, so everything here is 2 dimensions. Yes. Right, so everything here is 2 dimensions. Now, let's think in 3 dimensions. Yes, yes, in 3D, this is also an interesting open question to prove this math gap for the.
No, there is that's not. That's
that, yes, okay, but be more precise.
Upward marking.
Yes, okay, so, right. Thanks for the comment. Yes, being more precise is maybe an interesting open question.
Yeah.
All right, so what happens in 3D? In 3D, as we mentioned, that the conjecture is, if you look at the 2-point function, there is a magnetization. And on top of that, if you look at the truncated 2-point function, you have this Gaussian mode, and which means that asymptotically, it's like a covariance for the Gaussian free field. You have a constant divided by x to d minus 2. And this constant should also differ from the Gaussian constant because of this interaction of vortices. Tom and co-authors did a lot of made a lot of progress in early days in the 80s. Basically, we have upper and lower bound for the 2-point functions, and there is also work for the transversal 2-point functions, where it means that you look at the Gibbs state, where your spin model has a spin fixed boundary conditions in one direction, and then you can look at the spin-spin correlation in the other directions, sign-sign correlation. So in this work, they obtained the upper and lower bound for the transversal correlation with the 2 different constants. Now, so what's there is another impressive work which is very related to what we're talking about, is actually by a series of papers by Balaban, who showed, well, in the 80s and 90s, who showed that for very closely related models of n components, he managed to obtain, using very complicated renormalization group arguments, the spin-spin correlation, which would lead you to asymptotic 1 over x to the d minus 2. So this is not the proof that I understand. With Paul, we managed to give the proof of the conjecture for the Villain model. So dimension 3 and higher, low enough temperature, we were able to obtain that this truncated two-point function is exactly a constant divided by x to the d-2 plus a lower order term. And we were managed to see also that this constant is different from the Gaussian one. So it's not equal to the Gaussian one. This is the Gaussian one. It's not equal to that, but it's a small difference. The difference, occurs only with order e to the minus beta, basically. So we're also able to obtain this transversal spin-spin correlation as well. So got this sin theta 0, sin theta x, asymptotically 1 over x to d-2.
Is it the same coefficient? Between the
It should be the same coefficient, but not so clear from our argument. Because the other, so when you look at the other component, it's going to be a truncated two-point function. It should be much lower order.
Would it be exponential?
No, it should be another power law. So if you do a Gaussian computation, you see that it's something like 1 over x to 2d-2 or something. Yeah, it's another power law, but lower. I think in Thomas' paper, there is this correlation. Well, they use this correlation inequality. So we know that this one is less than the transversal one. So that's for sure. So we have but this is not a sharp upper bound because we know this should be of much lower order. Yes.
I guess that should indicate quite a bit fast, twice as fast, basically.
Twice as fast. Yes. Okay. Yes. It's related to the covariance of phi 0 square and phi x square for the Gaussian free field 3 dimensions.
So this naive intuitive pictures which physicists draw that you have exponential decay in the principal direction, that's not quite right. This Mexican hat.
Yes, will be nice.
You might think in the radial direction you had exponential decay.
That's what I meant. Yeah.
Yes. Okay. So I guess
But you also get which actually would be, I guess your result says that, but I just want to be sure. You get rotation invariance?
yes. Thanks for the comment. So yes, I mean if you see from this result, this is the rotation invariant. Right. So we're looking at the Villain model with the homogeneous coupling, so it should give you rotation invariance in the limit. Presumably, we can do more general couplings, which is maybe heterogeneous, and in that case, you have some Green's function, but not such a nice one. You have some Green's function which come from some operator, which there's this A bar which is not diagonal, basically. Okay, so
this all is going to be coming from some kind of homogenization picture, which I guess will explain, right?
yes, I would explain the proof. This is
what just ordinary homogenization is, first of all.
it's yes. Well, it's a Helmholtz-Strand equation, and you homogenize it. Yes. Maybe I'll use the remaining of the time explaining the proof. I hope it won't get you guys too bored. So the proof is certainly, as we mentioned, there's this Coulomb gas representation, duality argument, and then there is this renormalization going on, and finally we do some homogenization. First part is this Coulomb gas representation, which perhaps dates back in the physics literature by Kadanoff and co-authors, and then Tom and Jürgen Froelich have the rigorous formulation for that, which is that you can write the Villain model in terms of a Gaussian free field times a Coulomb gas. So, and then all the remaining work will be focused on the Coulomb gas part. Now, how does that work? Okay, we're in 3 and higher dimensions, so we need to distinguish different functions. There's functions on vertices, edges, and faces. So in particular, the vortices we're talking about are on faces. And what's important is for this step is this Helmholtz decomposition that you can write any vector field in terms of a curl-free, which is a potential field, and a divergence-free field. And you know exactly what this divergence-free field looks like. Okay, now if we start with this Villay model Gibbs measure, we can first, so M are the winding numbers on the edges. We can first exchange this order. We put M out, so M is now vector valued stuff. And so we have this. We have this measure, and then we can split the summation, total summation into two parts. So first of all, we can sum over for the M, which give rise to some fixed vortices. So Q are the vortices or faces. So we can first group the M's, sum over them with the fixed vortices, and then sum over all the Q's.
In 2 dimensions or general?
This is quite general, yes. Because Q is, in 2D, you know exactly how, well, it's very intuitive what Q is, but in higher dimensional, you can just define it by the curl of M.
So would this be vertex lines, verticity lines? Yes,
yeah, it could be, and some kind of, I think there are work by Froelich and Pfister, which they talk about some boundary conditions which can impose its vortex lines in your systems. But these things were not really contributed if we're looking at, I don't know, this translation invariant Gibbs state.
But you do have vortex lines, right? That's certainly how we think of it, you know.
Okay.
But these are not points.
Not points, they're not points, no, they're vortex lines. They're vortex tubes or lines, yeah.
But in this picture, at low temperature, the vortices are quite local, right? In this,
They're local, they're going to be low temperature, they're going to be short vortices, yeah.
short vortices, yes.
Short, you mean kind of
Short means the length is short.
loops.
That's the high temperature.
That's right. That's the low temperature case. There are no, yes. There are these Qs are tightly binding with each other, basically. So here, now we can apply this Hodge decomposition to rewrite M, all the M's in terms of the potential field plus divergence free field. And if you do that, you see this is orthogonal as well. So because this is divergence free, so the inner product is 0. So the Gaussian nature of this interaction is very helpful here. So you can just expand out. You have a part which only have a gradient of phi, the potential, and you have another part which has this curl of Q. Now you rewrite it. So this spins on the circle plus this gradient of phi would give you back the original Gaussian free field, and the other part by integration by parts, you see the Coulomb gas. This is how this duality argument works. Now this is the duality for the position function, but you can also do it for correlation function as well. So what you get is correlation function, 2-point function. You can write it as some observable in the Gaussian free field times the ratio of the position function of the Coulomb gas. So this one differs by this factor, which is your insert 2-point charges in the Coulomb gas, one at 0 and the other opposite one at x. This gave you this sigma 0x, which is the difference of the Green's function. And now what next one can do is one can use Gaussian representation for the Coulomb gas, because it's called sign order representation, basically, because this is the covariance structure for Gaussian free field. You can write the Coulomb gas position function in terms of Gaussian free field expectations. You can do that for both the numerator and denominator. Now, a quick remark that is this decomposition give you all the Q's, all the vortices with divergence Q equal to 0. So in 2D, this condition just means that the charges are globally neutral. And in dimension 3 and higher, this actually means that the Qs have a lot of local cancellations, which makes the renormalization argument a bit easier in dimension 3 and higher. So in fact, we can use the one-step renormalization to split out the Gaussian into a local part and a smooth part. So the red one is the smooth part. If we integrate out the local part, we get some prefactor which gets very small if Q is large and beta is large. So this sort of heuristically give you the picture that at very low temperature, the Qs have to be tightly binding with each other, have a lot of local cancellations. And then we need to understand this expectation of a smooth field. So you can do a resummation using the polymer expansion to rewrite this ratio as in the exponential. So this is basically the only object that we need to understand in order to understand the precise behavior of the two-point function for the Belay model.
So phi1 is the Gaussian mode?
Phi1 is the Gaussian mode. It's kind of a smooth Gaussian mode, but it's sort of non-local. So the Gaussian mode actually is a little bit different from phi1. You see, it should came out of the whole expression.
Okay.
So it's going to be yes, it's going to be some effective Gaussian measure, but not exactly phi1. Okay, so we need to focus on studying this big object. And
I'm a little confused about notation, but so you start with a local spin correlation, but when you do this duality, you get a kind of a string correlation. Is that right?
So this is a little bit. It's not exactly the same duality as you mentioned.
Okay.
So it's going to be a duality which gave you the ratio of the two prediction function of Coulomb gas.
Yes.
So directly working with this Coulomb gas thing, one with the two extra charges, one without.
Yes.
And you have so everything you can write using sign-Gordon representation. And then what we do is we first use a one-step renormalization to integrate out the local mode. And after that, you have a remaining Gaussian, which is smooth and global. And you have to study this this thing, which
So what's your expectation? I don't quite understand your expectation.
okay. So this phi1 is so this is the smooth Gaussian.
The free field?
This is yes. So this is a free field with a covariance written as a red one. So this is we integrate out the local Gaussian. Okay, it's not the free field.
No, so is it massive?
It's a little bit massive. Like, well, yes. I mean, it's in that. Okay, I guess not really massive. Okay, this one is massive, right? This is a local mode of the free field. So if we integrate out, we have the remaining covariance like this, which is essentially like a free field, but not exactly. So
well, if it's just the covariance, it's free field. But the question is whether the free field is massive or not at this point.
I don't think so. At this stage, it's not massive, right? This is like logarithmic, so this is like 1. So you have a log minus 1.
I see. It's that minus that. It's not the inverse.
That minus,
Okay.
yes.
So that's of course
That's just the
that's mathless. Okay.
yeah, that's still mathless. But you
And it's still you still have a free field.
you have a free field, a bit different covariance. Yes. Okay, so we want to understand this ratio. For that, we can do a change of measure.
So wait a minute, what's the ZQ? So that's also something I have to going a little fast for me.
DQ is arising from this very small things, which is when you integrate out the local mode, you see that there will be a rapid decay if the Q norm is big.
Yes.
So that gave rise to the ZQs. So you resum over all these that is animal kind of things. You can rewrite the summation in terms.
That's just that weight, you're saying. The DQ is just that weight.
Yes. So it's kind of preferring dipoles, basically.
Okay.
Yes. Rewrite it into that, and we need to understand this object. So to do that, we have this phi 1, which is some kind of free field, but on top of that, there is also this contribution, which is like a dipole, but you also have contribution for all possible Qs. So this is how things would end up with when we rewrite this in terms of the measure, which has everything. So this measure has first part is this essentially Gaussian free field object. And the second part would be the perturbative term, which come from this whole one-step normalization argument. So it looks fairly intimidating, but okay, why are we doing this? So the reason is after doing all these steps, this measure looks complicated, but you would see that for beta large, the leading contribution would just come from the first term, which is the ordinary free field, and the remaining part are act as a perturbation term. So in fact, this measure is still a log concave measure. So it makes tools from a PDE and homogenization to be applicable here. And also, when we end up with this measure, the observable we have is also a complicated and non-local thing, a lot of sines and cosines. But with the tool from PDE, we're able to give a precise asymptotics of this.
Okay. So I think an important point to make here to see that it is convex is that Q is
it's like gradient.
It has a total average 0, right? And it's small.
Yes.
It's like a dipole gas, right?
Yes, it's like a dipole gas. So this is like having the condition divergence equal to 0. It gives you a lot of local cancellations. So essentially, you can think of it as a gradients. Well, it's always a balancing Q, and for majority of configurations, Qs are just binding as dipoles.
This nearest neighbor or
Just,
very short.
that's right. Yes, very short and nearest neighbor thing.
And that's the difference between that and the two-dimensional case where you can have potentially long dipoles, right?
Yes. Also,
the weights wouldn't be very fast.
That's right. And also in 2D, it's not really clear how to make this argument work, that you can integrate out one step and you have some effective log concave measures. That for this to work, we also need to use the fact that Q has a lot of local cancellation in 3D. So this renormalization part is also not clear in 2D. That makes 2D problem harder. Okay, so maybe in the remaining time, I would try to describe how the arguments from PDE and homogenization theory can help to give a precise asymptotics for this object. So let's okay, this is complicated, but let's look at something which is a little bit a toy model for that, which is the gradient field. So instead of having so let's look at this Gibbs measure. Which depending on the gradient of phi. So if V is a quadratic function, this is just the discrete Gaussian free field, which we know very well. In particular, the covariance there is just the simple random walk-Green's function. Now, what happens if we took a more general V? So, for example, V is a uniformly convex in the sense that the second derivative is bounded from above and below. Well, so there's still something analogous there. So you don't have a simple random walk anymore, but you can write the covariance in terms of another Green's function, which is more complicated. So this is called the Helmholtz-Stokes representation. So in particular, if you have this generic gradient model, you want to understand the covariance of two functions of phi's, you can always write it in terms of this summation, where the partial x is a derivative over the field at x, partial y derivative of the field at y, and L is some elliptic operator, which is infinite dimensional. So what is L? So in particular, we can write L into two parts. The first part is this delta phi thing. Now, what is delta phi? So it's defined here in terms of the partial phi x. Probabilistically speaking, you can think of that as generator for the Langevin dynamics, and in particular, you see that this is self-adjoint with respect to the Gibbs measure, and it's kind of infinite dimensional.
Phi is a little bit mixed up here, right? I'm trying to think through this. Well, maybe what is the ddx? It means dd phi x, or
this is dd phi x, yes. So yeah, this is the derivative of the field, and so in some sense, this is infinite dimensional operator, which acts on all the spatial locations.
So the adjoint in the first line means with respect to the Gibbs measure?
With respect to the Gibbs measure, yes. So it just means this. You can do the integration by parts when you have a Gibbs measure. So yeah, it's also clear from the probabilistic case because of the Langevin dynamics generator. On top of this operator, we have the usual elliptic operator. A is just the second derivative of the V. And now you see why the V has a second derivative bounded above and below helpful, because that means this part is uniformly elliptic. So this is a normal uniform elliptic operator living on the space of ZB. So combined with each other, L is some elliptic operator, but infinite dimensional, and its coefficient is random, right? This is depending on the random field. So so we have this Hafer-Stillstrand representation here. So a special case here is that if you look at the covariance of 2 points, phi x and phi y, this is simply the average of the Green's function at x and y with respect to this operator, Hafer-Stillstrand elliptic operator. And therefore, if you want to prove macroscopically the field has a Gaussian behavior, it will be very helpful to understand the solution of elliptic equations with respect to this L operator. In particular, if you look at the Green's function, that would give you a 2-point function of the original gradient model. So a very heuristically, what you want to prove is the Green's function associated with L.
sorry, what's your omega? Is that what's omega here?
So omega is basically the space of your field. This is yes, the phi of x is it for x. So every function here has a dependence on the spatial location and or the random field. So that's basically what this notation means. Heuristically, to prove a convergence to a free field, it would just mean that you want to study the Green's function for this original problem and to show that on large scale, it behaves like the Green's function for the operator, elliptic operator with constant coefficient. In particular, if you can get a rate of convergence for that, which is much smaller than the original Green's function in dimension 3 and higher, you obtain some rate of convergence to the Gaussian. Now, this is a heuristic. So let me try to board you with a slightly harder computation, which is more relevant to the study of the Belay model. So at very low temperature, we see that we can simplify this complicated expression from above by some kind of expectation with respect to this object, which have a lot of sines and cosines. And here the phi sigma 0x is the Green's function at 0 minus the Green's function at x. Okay, so you have this thing. Now you can rewrite this as the expectation for each of them plus their covariance, right? Each of them, you will see that they are the same because of the translation invariance. In fact, that gives you the magnetization squared. And now you need to understand how their covariance decays. So one short because heuristically we believe that
that G is the full Helfer-Schuster Green's function, or is it the
G is the simple random Walk-Green function.
Okay.
That's the simple yes, this is the simple random Walk-Green function. So these part are nice, but there's also this oscillating function of phi, basically the sine of phi q, which you can think of as a gradient of phi. Now at low temperature, as we said, that Q essentially forms dipoles. Approximately, you can think of your problem as computing the covariance of this kind of non-local observables, which involving sine of grad phi's. Okay, so how do you do that? If you just apply the Helfer-Schuster, you see that you took a derivative here, or took a derivative here, you create a Green's function. So it gave you basically the cosines and the second derivative of this Helfer-Schuster Green's function and times the remaining exponential things. Now, if we can show that the convergence of the second derivative of the Helfer-Schuster Green's function converges to some ordinary Green's function second derivative in a pretty strong sense, in the sense that the remaining error is of a much lower order, we can approximate the expression by something like this. So these are simple random Walk-Green's function. This is essentially some kind of simple random Walk-Green's function. This is another simple random Walk-Green's function. By explicit calculation, you see that would give you constant divided by 1 over x and e minus 2. And in particular, you see that we really need this error term to be of a smaller order to show that this would not affect the leading term, which is 1 over x and e minus 2. So this gives another heuristics object to prove is that, okay, what we want to show is not only the Green's function converge, but also the second derivative of the Green's function converge in a pretty strong sense. In fact, we need a moment a bit higher than 2. So these objects behave like 1 over x to the b, and we need a faster rate of convergence.
So wait a minute. So let me just make sure I said the first G is the Helfer-Schuster Green's function.
This is the Helfer-Schuster Green's function.
Okay, and the other one is
the
normalized
limiting Green's function. Yes.
So that's an ordinary Green's function.
This is ordinary Green's function. Yes. So that's what basically what we need to do. Now just okay, historical remark. So Helfer-Schuster representation was first done by Helfer and Schuster, but Tom was actually first. Tom and Nadab Spencer, also in this Nadab Spencer paper, was first introduced this technique to study the Gibbs measures, and there were also the work of Jacomi, Euler, and Spohn, who took a point of view parabolically, dynamically, and in these works, the homogenization of this Helfer-Schuster equation to a constant coefficient equation has been established. There's not so much information about the rate of convergence. With Scott Armstrong, we actually obtain a rate of convergence for these Helfer-Schuster equations, and we use that to obtain knowledge of the regularity of the surface tension of the model. The basic idea to prove a homogenization for us is we are following this approach of Armstrong, Kusi, and Murat. So basically, we know that the solution to elliptic equation can be characterized by the energy quantity, some kind of generalized Dirichlet energy. So in order to know the solution converge, we actually show the energy converge. And for that, we need to understand basically the energy quantity at every given scale. And the energy quantity at every given scale would, in fact, also give you the effective diffusivity at every given scale. It's another kind of renormalization going on that you have. You look at the information up to each given scale, you find the effective diffusivity, which corresponding to the information at that scale, and you want to show that this one converges when your volume goes to infinity. And in fact, there is some approximate subadditivity property for this thing. So it's not too hard to show that these effective diffusivity converge. But if you want to have a rate of convergence, it's better to have some mixing property. Basically, everything defined here would rely on the underlying random field, which happens everywhere. So you want to say that if I change the random field in the distant places a little bit, maybe the effect on the quantity A in the faraway place does not change very much. So this is some kind of a mixing condition are needed. And to date, there are quite a few different approaches in order to prove a mixing. So the first one, which in the paper of Gloria Otto, which is also inspired by an unpublished note of Tom and Nadaf, is some kind of you get mixing using some spectral gap assumptions. And it's kind of related to us, but not quite, because we're in infinite volume. So there's not really a spectral gap there. And another possibility is to do some kind of dynamical coupling to get mixing. So you're coupling a Gibbs measure system of different size. You run the Langevin dynamics and couple with them with running by the same Brownian motion, and you compare the difference of them. So this approach was done first by Funaki and Spohn, and then later some refined version was done by Jason Miller, and also in my paper with Armstrong. And in the paper we did with Paul, we were actually using some knowledge of the second order Haber-Sylstrom equation, which I'm gonna explain in a minute. You can also do it by understanding the heat kernel of the associated diffusion and proving some regularity theory of it. Now, so what did we do in order to obtain the mixing? Is that we start with a very complicated Haber-Sylstrom operator, but in fact, we can see that if the temperature is low enough, the leading term, as we just see, is the standard elliptic operator here. The other things are like acting like a perturbation. And therefore, you would expect that if beta is large, the solution is kind of close to the harmonic functions. In fact, the harmonic function has a very nice regularity. So we also use that to obtain that the solution to the Haber-Sylstrom equation has a very good regularity, C0, 1 minus epsilon. And as beta go to infinity, it becomes better and better. So that gives you a decay of the Green's function associated to the Haber-Sylstrom equation. Now, what we need there, we need a little bit more than that, because we want to know that whether the energy quantity or the solution in the local problem here, does it feel the influence from the change of the field in a very far away place? Therefore, we would also want to understand the derivative of the Green's function with respect to the random field. So to do that, we just took a field derivative to the equation. You obtain a higher order equation, basically, but you see that the leading term of the new equation is just you took this partial and it will go inside your Laplacian. So you got the leading term is still a Laplacian term, but then you have a term which interact with this complicated perturbation operator, which give you a lot of commutators and some other higher order terms. So you obtain a higher order equation, which we call this second order equation. And you can see that the operator here is still going to be a Laplacian plus a perturbation term. And therefore, we can also establish a very good regularity of the solution of these equations. So that would give you that the derivative of the Green's function actually decays in some power law if your distance from the y to your problem here is far away. So that's how we obtain some kind of a mixing and obtain a rate of convergence of the solution. So okay, that's pretty much what I want to talk about. Maybe I'll just use my last slides to list a bunch of open questions. So there's plenty of open questions in dispute. There are some cases where rigorous Coulomb gas representation has been established largely by the work of Tom and co-authors, but the renormalization argument hasn't been quite nicely carried out yet to give the very precise information of the correlation of the model. So these things are largely remains open, and there is even more wildly open case of other models where there are some physics argument of the Coulomb gas, but it seems like to formulate a rigorous version of the duality and the representation are still yet to be done. So I'll just stop here.
Any question to Wei?
And what, is it possible to do more than one step of the renormalization?
So the thing is, here, one step makes us already happy because dimension 3 and higher, one step gives you the convexity. So when you have a convexity, it's we have the right tool to analyze them. In 2D, of course, it's very different and much harder because basically you need infinite many steps of renormalizations, and after each step, it's still not convex. So that's why the 2D cases are still difficult. But for some cases, like this work of Pierluigi Falco, he has an impressive way to carry out this infinitely many steps.
So the slide is closed.
Okay. Yes.
So your results are symptotic in beta going to infinity, but also x going to infinity, right?
So this result is for finite beta, but very large. So so there exists a large beta 0, such that above that, we have all these asymptotics as x to infinity. Yes.
Can you comment a bit on the distinction between taking a scaling limit, which I presume you have not done, and the homogenization? I mean, is it the end result is sort of the same? No.
Okay, so in fact, in this regime where temperature is very low, you expect the scaling limit of this fluctuation is a Gaussian free field. What we did is we characterized the 2-point function, which converges to the covariance of the Gaussian free field.
Would you have done the 4-point function too, or?
We haven't done that in our paper because it's like too technical for us. But we expect the same argument would work. If you took 4 macroscopic away 4-point function, you should be able to show that it factorizes. Yes.
So I have a question about this Coulomb gas. So can you comment on the difference between these two lists? So what do you mean by the first list is rigorous representation established, the second one is yet to be.
So there's, for example, in this U1 case, there's a work by Tom, Jürgen Froelich, and co-authors that you can write the spin-spin correlation in terms of some very explicit quantity of the lattice Coulomb gas. So that's kind of a sort of rigorous reformulation of the problem in terms of Coulomb gas. So you have a well-defined question.
Before taking the scaling limit, right?
Before taking the scaling limit, on the lattice level, you have a well-defined question, right? The one there, all the things I think is kind of vague there. I mean,
but there, like in the lattice level, we also have some precise mapping to some height function.
There is some height function mapping, but I think what these people, well, in these works of the Coulomb gas representation, they're just writing down some continuous field and they claim this Coulomb gas thing there. So it's more on the level of the maybe the paper of Kosterlitz-Thouless, not on the rigorous level. So that's
So you're saying that they have this lattice level correspondence, but I don't know the scaling limit.
okay. So this part, you have a lattice level correspondence. We have some knowledge of the scaling limit, but it's not very precise. This part, I think the lattice level correspondence is not rigorous. So
I wouldn't say the lattice level one is rigorous, but it's like you cannot use it to effectively get much on the scaling limit, probably. But on the lattice level,
okay, so we can talk more, but I have the impression that this there's no well-defined correspondence, for example, for the covariance and the Coulomb.
Okay, yeah, maybe we can talk about
Yes.
offline.
Okay.
So I have another question about these ratios that you mentioned. Can you go to one of the slides? So you have a ratio between these.
Yes.
And, equal to a Gaussian free field plus a perturbation.
Yes, something like that.
Maybe it's slightly below this. So you have a
Okay.
like write it as a Gaussian free field plus a perturbation.
Yes.
The perturbation is kind of a lower order than. And this, so
Yes,
whether these have a scaling limit, like
Yes, so they also contribute in the scaling limit.
field theory description.
Okay. In some sense, not. In this case, you have a lattice problem, and I think you have a Gaussian free field plus a perturbation like this. But in this case, basically they would flow to some free field with a different covariance. So in this low temperature phase, the continuum field is just Gaussian. The high temperature phase, maybe there is something. Maybe there's some Stein-Gordon-like field appearing in the continuum.
So you mentioned these different approaches to homogenization and
Right.
This coupling method that Spawn and Ola use, would that apply here or not?
It's not so.
Not quantitative enough?
Well, it's not so clear for us, and therefore we use a different approach. Yes, I mean.
So I don't know what they did, but they get some quantitative version of.
So in the paper of Funaki and Spohn, they are not very quantitative. They're studying the hydrodynamic limit. So you don't really. But later in the work of Jason Miller, so he has very refined estimates.
And then that might be strong enough.
That's strong enough. Yes. I guess our feeling is that there may be some problem to carry this out for the vector value thing. So it should not be maybe it's just a technical issue, but I mean heuristically it should carry out, but on the technical level there's some problems. I guess, yeah. It's a very natural thing to do, but so far I guess it only works in some limited case. In fact, if you have a potential like a Stein-Gordon kind of things, we also don't know how this would carry out.
Any other questions? Okay, so if there's no question, let's wait.